now we're going to cover a little bit about electronic symbols. Now this is just a little taster of the common electronic symbols you might encounter. Certainly our design engineering students are going to need to know most of these, or pretty much all of these. We're not going to cover a great deal about some of them, like capacitors for example, but you need to know what they do at the very least. So we'll start off on the left here. We've got switches. Now they come in different shapes and sizes, but we've got push switches or momentary switches, which means they won't stay in the state that you just activated. So you push to make, in this case. This will normally be open, so you push it to close it. And this is called push to make. So you push to connect this circuit, and then when you let go, it'll disconnect and be in this state. Normally open, it's called. Normally closed or push to break. They can look identical to each other, but they'll be just written as a different specification. Because when you push the button, you'll break open that circuit, so you'll switch something off. And then when you let go of the switch, it will spring back like that. Now, being momentary switches, the other type of switch, like a light switch in a room, is a latching switch. Now, these stay in the state that you've left them. So in this case, we often see these terms here, SPDT or SPST or DPDT, as is this one. What that means is single pole dual throw, or single pole single throw if it's an SPST. Now a single throw would not have this one here. It means single pole means there's just one connection being made, so it's just one circuit being dealt with. Now a dual throw is pretty much as good as a single throw. You just don't have to wire one of the third spades up, because what happens here, in one state it's connected this way, but if you didn't have this wired up to anything, it would be on or off. So it's quite good having a dual throw thing like that with a common in the middle. So this one here, you'll notice it's got on and on written. You can have it on that way or have it on that way, depending on which way the toggle is. Okay, so single pole, it's just one circuit. Dual throw, two options. Here we've got a dual pole, dual throw. Now you'll see there's two rows of spades here. So you've got two totally independent circuits being switched on by a single flick. Okay, so they can be quite useful for more common circuits. Now you might even find 4-throw or 5-throw rotary knobs, or they just have a massive great bank of spades depending on which poles are being switched on and off. So yeah, many different types of switches here. Now we'll cover this later on, but a relay is basically one of these latching switches that is electronically switched on by an electromagnet. But we'll cover that in a minute. On to resistors. Okay, we talked about resistors in the last episode. They're used to restrict the amount of current, and these are the very common standard through-hole resistors that you might come across. Through-hole means that you poke the wire through actual holes in the circuit board and solder them on the other side. They're the traditional way of doing it, as opposed to surface mount, which is a much more compact and modern way of making very miniature electronics. But generally, through-hole is a lot easier to solder up by hand. It is possible on surface mount, but it's quite fiddly. Anyway, standard fixed resistors have these color-coded bars, which we'll cover later on this video, but they're used to determine what resistor value they are just by reading the color codes. And then variable resistors, same as a fixed one, but there's a little thing in the middle which you can turn, and you can change the resistance depending on where you turn it from its minimum to its maximum. Now these tend to be rare because generally you'll have something called a potentiometer, which has got 3 spades instead, or 3 pins. Now what happens here is you've got the full value of a resistor, say this is 10,000 ohms, across these bits. So if you connect the 2 outer pins like that, you'll get the maximum resistance that this thing is set at, often 10k they're called. And then the middle one is determined by turning this knob, and it's called a wiper, and it'll basically go from the minimum to the maximum range. So you get possibly as little as 0, but probably not, up to 10k just by turning this knob. Now this is really useful for basically setting a voltage. So if this is connected to the positive and this to the negative, you can turn the knob in the middle and you can get 0 to whatever voltage you've got. And this is often used in something called a potential divider, which we're going to cover in a later episode. It's a really useful thing to do. So it's a form of variable resistor called a potentiometer because it has 3 pins, and you can choose that middle value between the 2 maximum ones. Okay, other forms of resistor, there are many different types of environmental sensors that change their resistance. Here are the 2 most common ones. Light dependent resistor, which is this symbol here. So do take note of these symbols whilst I'm going through them. They're useful. Certainly our students will need to know them in the exam. But these are the most common ones you should know. LDR, it's a resistor symbol like this with a circle around it and 2 little arrows depicting light going into it. Okay, and these will change their resistance. Again, we're going to cover these in more detail in a further episode along the way. And then the thermistor has this kind of kinked line through it like that. And they come in all sorts of different form factors, but generally little capsules, encapsulated ceramic things. They look a little bit like these ceramic capacitors as well. But yeah, these will change temperature, change resistance as the temperature changes. So we'll cover those in more detail later on. Diodes, they're a very important thing to learn about. They're effectively a one-way valve. Now, provided you don't exceed their voltage, they will stop current going in one direction. Now, I've actually put the symbol and the photos the other way around. So this bar here, almost think of it like a no entry sign, a stop sign. Now, the idea is the current cannot go this way. The arrow is another clue like that. So the current goes from positive here down to negative that way, but not the other way around. Now, on these little diodes, they've got bands on them, which should be the other way around like that. So this bar here corresponds to that. So this is positive and this is negative on a diode. We all know what these things are. LEDs, they are actually diodes as well, so they only work in one direction too. Now you might notice one of the feet, one of the little legs is shorter than the other one, or you might find there's a little notch across this wider bit, this flange. So a little notch chipped off on the negative side, just to tell you, okay, less flat, negative. So that bar there corresponds to that notch. That is the way to connect them. They won't work the other way around. So you need to make sure they go one way round. So LEDs. Capacitors, I mentioned before, they look a little bit like these thermistors. These are ceramic capacitors, and they tend to be of a smaller measurement. And farads is the measurement of capacitance, which is basically, consider it like a very rudimentary form of battery. It stores charge. Now, it's not actually used like a battery, like a rechargeable battery. They'll be used to smooth out and sometimes delay things switching on as well. So we'll generally have them smoothing out spikes in noisy circuits. If you've got a motor or something like that, you might use a capacitor across the motor just to take out any spikes, because they will very quickly take up that charge but slowly fill up. As well as that, they're actually used as timers as well, because they can take a bit of time to charge up. And we won't be covering that in this series, but they are quite useful to go alongside timing chips like clocks. A common one that's used is called a 555 timer, and you'll use that alongside a capacitor to determine how quickly it pulses by the time that these take to fill up. And then if they're of a bigger order, they will actually have to be one way round. So these barrel shaped ones come in all sorts of sizes, right up to this size. They have a plus sign, so they need to be the right way round as well. So you'll notice this band across it is normally a negative to depict which way round. Now, big ones like this, you've got to be quite careful with them, because they can discharge very quickly as well. So you don't want to be touching a large capacitor like that that's charged. It'll give you a nasty shock. But anyway, these are called electrolytic capacitors, and they're generally a bit like a battery symbol, but both bars are the same width, and they're a bit more chunky than a battery symbol. Okay, and then on to transistors. So we've got two types here, well, four types. We've got NPN, which is this one, or PNP, which is this one. Now, you don't actually have to know that or how they differ, but you might see two types of transistor like that. I generally find if you're talking about simple output transistors, this one kind of makes the most sense, because you get a small amount of charge on an output here, and it will amplify it. So you can use a small amount of current to switch on a much larger amount of current with a transistor. So they can be used as electronic switches, but they're also used as amplifiers as well. The way of remembering this, I find, is NPN is not pointing in, N not P for pointing, and well, there's an N in. So obviously the arrow pointing out, that means this is NPN, and yet pointing in, PNP, is this way around. But in this episode, or in this series of videos, we're not going to go into a great deal of detail about how these work. But transistors and MOSFETs are basically electronic switches. So they'll take a very small current and amplify it and switch on a much bigger current. Now that can be used for literally amplifying a little signal or a sound or something like that, or making a decision from a very small microprocessor delivering a very, very small output current can be used to switch on something a bit more useful, like an LED or something else, mechanical switch or something like that, which are these things here called relays. Okay, so these here are outputs, and generally, well, there's going to be another video further down the line where we'll cover these in more detail. But we might have DC motors, straightforward thing like that. Stepper motors, in this case is a bipolar stepper motor with 4 wires coming out of it, or a servo with 3 wires coming out of it. Relays, consider like a switch and an electromagnet, so it'll electronically switch on a much bigger circuit or something like that. So if you've got a little tiny electronic control, a little microcontroller with a tiny little output current, and you want to switch on a big, say, mains voltage, what you might use is a combination of amplifying that switch. So you start off with a little transistor, which is capable of switching on a current, capable of energizing this coil, which will then switch on a much bigger switch like that, like a mains voltage. These are relays, and then in a similar way, using an electromagnet, instead of switching on a switch, you can have a solenoid, which is just a physical actuation which will push out a little thing, switch on a latch or something like that. But yeah, there you go, electronic symbols. Like I said, there's plenty more, but these are the basics you should know in your exam. Let's have a look at how to read a resistor from the bands on it, the color coding. It's a pretty straightforward way of reading it when you get the hang of it. Takes a little bit to get used to, but here's what we've got. So most resistors have got 4 or 3 bands here, then they've got a gap, and then they've got a band on the end. Now almost always this is gold, but don't take it as a given that it's going to be gold. It might not be, it might be red or brown, which will confuse matters because these are always various colours. It's normally the way you look at it straight away and see the gold side, because it's the only one with tolerance on it. However, don't take that as a given. What you're really looking for is the gap. Now, some resistors have got 3 bands and some have got 4 bands. This third digit is the one to ignore if it's only got 3 bands. You're always, the last band before the gap is always going to be this multiplier. The way it works is you read off colours, so 2, 4, 1000. Say if it's red, yellow, and then orange. So you're going to look 24 times 1000, 24,000. It's as simple as that. So let's have a few examples. This one here, you see the gap. So obviously, like I say, most are gold, but we're looking for the gap here. So we're going to spin it around. We're going to read brown, which is 1, black, which is 0, and red, which is 100. So I'm saying 10, 10 times 100 is 1000. Okay, so that's a 1k ohm. What about this one? Green, blue, brown, gap, gold. So again, we spin it around, looking for the gap. We've got green is 5, blue is 6, brown is 10. So 56 times 10 is 560 ohms. That's a pretty easy one. These two are pretty easy to get your head around. What about this one? Now, really, this is where it gets confusing because they haven't really put much of a gap between the gold. Obviously, like I say, given the fact that none of the numbers are gold, we can assume that is the tolerance this time around. But you shouldn't really assume it to be the tolerance, certainly if it's going to be a different colour. But if this was a different colour, you might want to get a multimeter out and work it out. Anyway, this one is 4, yellow, purple, 7, and red, 100. So 47 times 100, 4,700, which is a 4K 7 ohm resistor. What about this one? Now, we haven't got a gold one here, and we've got 4 bands. So I'm looking for the gap. This one looks bigger than that one. So I'm going to spin it round and read off a yellow being 4, purple being 7, it's 0, so we've got a third digit. We're just reading another table like this. So black being 0, and then grey or brown, I'd say brown, times 10. So 470 times 10 this time. So 3 digits, 470 times 10, 4,700. So these are the same 4K7 resistors, but because it's a 4-banded number value, you're going to have a different colour scheme because you've got one less multiplier here. You've got one more digit and one less factor of 10. So that's where it gets a little bit confusing. Fortunately, most of them are 3-band with a gold little bit on it, so that makes life a little bit easier to read. But sometimes you might have some like this, so just bear that in mind. So in addition to using colour charts, the resistor tables, you should be able to use a multimeter as well. Being a name multimeter, it measures a multitude of different electrical things, so one of which being resistance. This band here, in the case of this budget one, by the way, these are very good and indispensable if you want to do electronics yourself. They're not expensive, but a nice robust multimeter. It goes from 200 up to 200 million ohms. So these more budget ones, you do have to select the range manually. The more expensive ones will just automatically choose the range. So we'll try with this one first. Now, if I start at the bottom at 200 ohms, if it's bigger than that amount, so bigger than 200, even if it's 201, it will say open circuit, OL. Okay. So I'll go up to the next range, OL. Next range, OL, 200k, OL, 20 mega ohms. We're beginning to get an amount there. Right, so I say 0.32. By the way, if you notice, if I hold it with my hand as well, I'll get a completely different reading, especially when you get into the big amounts. Okay, so I am a resistor and I'm making a big difference on that big resistor. So it's a good idea just to touch it with one hand like that. Touch it with one probe, not touch it with both hands like that. So yeah, what have we got there? We've got 0.32 thereabouts. What does that mean? Okay, so that's less than 1. So we're not in 1 million. So this will go from 1 to 20 million, or rather a fraction of 1 up to 20 million. So 0.32 is going to be the next unit down, in which case it's going to be in the 100,000. So 0.32 is 320,000 thereabouts. So that's how you would measure it in that range. Just to confirm that, we've got orange, yellow on this one. I don't know if you can see on the camera, but orange 3, and yellow 10,000. So 33 times 10,000, 330,000. Let's try a different one. Let's try this one now. So, oops. Again, if we're starting high up, okay, I've nearly got the right amount there. So I've got a figure, but it's very small. If you're into the 0.09, then you might want to go down a range like that. If it says nothing, let's say if we were in too high a range, it might just say nothing. We'll try it with a smaller resistor anyway. But I'll go down to 200k and I should be on the right amount. Yeah, sure enough, 99.3. Again, if I touch it with my hand, I'm going to get quite a considerably different reading there. So remember on the big value resistors not to touch it with two hands like that. 99 in the 200,000, obviously 100,000 there. That's more of an easy one. So double checking that. Brown 1, black 0, and then yellow 10,000. So 10 times 10,000, 100,000. Let's try another one here. So now, again, we're in a similar order. I'm going to go down. So it says 3.7 in 200k, so it should be 3,700k or thereabouts. But I might get a more accurate reading here in 20k, because it's still less than 20k, 3,700. And sure enough, I've got another decimal point there, so I've got a little bit more accuracy there. 3.84. Again, orange, white, red. So that's 3, 9, and red 100. 39 times 100, 3,900k. Or sorry, 3.9k kilo ohm resistor. If you're starting off on a big range like that and you get a smaller resistor, let's say this one here. Again, I'm still not picking up that small resistors, but let's say if you had a 300 ohm resistor and you're up in a 200 mega ohm range, it's just going to come out 0.00. It's going to think it's a total conductor there, so you've got to turn it right down, work your way down until you get a decent range. Now another really useful feature on these multimeters is this mode down here with the diode symbol and the sound thing. And what that is called a continuity tester. So you've got an audible beep, and you can tell when there's an electrical connection. It's really good for fault finding things. So say you've soldered this up wrong, and you might have some pretty kind of messy soldering. You might not know whether there's an electrical connection interfering with the adjacent pin, but you can just go across, and if you get a beep on two adjacent pins, you can see if they're meant to be connected or not, and if they're not, that might well be the fault. So you can see where things are electrically connected where they shouldn't be, or vice versa. So for example here I might be looking for a fault on the positive rail. For some reason there might not be a positive connection. I can hold that there. Actually it's that one, sorry. And yeah, I can check all of those positive terminals are connected up just by hearing that beep. It's a really useful feature, that. So when using it to measure voltage, what we do is, like with resistance, we choose the correct range. Now I'm using 4 AA batteries here, so it's about 4 to 6 volts. So similarly, I'm going to go to the next highest amount, which is 20 volts. Now here, I'm measuring across something. So in this case, this little motor is running away. I want to be careful not to short these wires, but just touch either side of it. As you can see, I've got the red and the black the wrong way around. It's coming out negative 4.36. So I'm measuring the potential difference across this motor. It's not quite the same with current. I mentioned it in the last episode, but basically what we need to do is create part of a circuit with these wires. Now what I'm going to do here is change this plug here to 10 amps. Now just look at the warning as well. We're doing quite a small kind of current. I'm not really worried that this motor is going to draw 10 amps. But if you are doing something that's got a slightly bigger load, you might want to just be careful not to run it too long through the meter, especially because it's not fused. So what we do, we'll just take one of these wires out, the positive in this case. We're going to add another jumper wire, like that. And now I'm going to switch this down to 10 amps. And you'll notice the motor, obviously I've broken the circuit like that, it's not working. But then when I hold the wire together, like this, oops, it works. Again, I've got them the wrong way around, but you can see I'm drawing 0.03 amps, so 30 milliamps on this little motor. Okay, so yeah, we use this 10 one down there, it's the biggest range that we use, and then we swap the plug around. Just remember to put it back, because most other functions use this plug in the middle. That's it for this episode. Next episode we will be doing some through-hole soldering, so we'll be making our genies.